This is a lesson on probability, again using permutations and combinations as we did in the previous lessons, just an extension. Two questions that are considered relatively complex, relatively difficult, particularly the last one. So let's see what we can do with them. The previous lesson introduced the concept of using permutations and combinations to solve probability questions. Here I will also use both methods just to keep them in front of you and shut me down at any point and work through the questions and then start me up again and then compare your answers. This first one, a bag contains 6 red marbles and 10 green marbles, and then from the bag 2 marbles are drawn out without replacement, and we want to get the probability of drawing 1 red marble and then 1 green marble, 1 red and 1 green marble, and then at least 1 green marble. So 3 questions on these. Now I'll go through it bullet by bullet. 1 red marble and then 1 green marble. So this is the probability of red then green. Now the word, I'll write that in English maybe, probability of red, green. Key word is then, because this implies that we do not have, or it tells us fairly clearly that we do not have to do the reverse order. And I'm going to do this one by the fundamental counting principle and then maybe take a look at it with combinations. But this is definitely one that lends itself to fundamental counting principle because its order is given within the group. And to select a red marble, there's 6 red marbles there out of a total of 16. So there's your first draw. Then the next one is to get a green marble, there's 10 green marbles out of a total of 15 because there's only 15 marbles left. And then if you reduce these two down, and some of you would just key it into your calculator and go from there, and that's okay. I'm going to reduce it by dividing by 5 like this. I'll divide the 2 and then the 2 will give me an 8 there. I'll divide by 3 and get a 2 there. And look at this, divide by 2 is 1, divide by 2 is 4. So when all is said and done, we end up with a probability of getting 1/4. Now in my mind, that's much easier than trying to use combinations because when order is suggested or told, then combinations is based on the idea that you do not care about the order. So if you use combinations in this, it would give you red and green in any order. So you have to watch it with that. And of course that in fact is the next question, 1 red and 1 green. So the fundamental counting principle would be the probability of red-green or green and then red. Now we already know that that's 1/4 from the previous one, so I'm not going to do that again. But then to get green, you would get 10 out of 16 multiplied by 6 out of 15. And I'll leave you to do the work on this, but you're going to get the same numbers, so you will end up with 1/4 plus 1/4 is 1/2. I like that method, at least for setting it up. But combinations will work because there's no specification of order within the group, so there's no risk. By the way, this previous one, you could use the question before this, you could have used permutations. I should have mentioned that because order was specified. But again, fundamental counting principle, great way to do it. Now with combinations, you would take a look at red-green in any order and consider that the number of ways to select 2 marbles would be 16, choose 2. The number of ways, that's the total, and then the number of ways to get the ones we want. To get 1 red out of 6 would be 6, choose 1. And to get 1 green out of 10 would be 10, choose 1. And then work this one out, and you should also get 1/2. You need to make yourself comfortable with these so that you can make good choices on this and not do anything too weird. The next bullet was at least 1 green marble. and at least one green marble, you could work out all the possibilities. And the words "at least" is always a troublesome thing because you know that you're going to get more than one possibility, or you expect to get more. So at least one green would mean that you have a green on the first draw and then a red on the second. Or the probability of red on the first and then green on the second. We've done both of those, by the way. Or the probability of getting green on first and second. Now this would be 1/4 plus 1/4 that we have previously. And then green and green would be 10 out of 16 multiplied by 9 out of 15. 10 out of 16, the number of green on the first, 9 out of 15 for the second. And then reduce away. This would be 2 and this would be 3. Divide by 3 is 1. Divide by 3 is 3. And I would say we can do one more. Divide by 2 is 1. Divide by 2 is 8. So we end up with 1/4 plus 1/4 plus 3 over 8. Get a common denominator of 8. So 2 over 8 plus 2 over 8 plus 3 over 8 is equal to 7 over 8. And I did stick to fundamental counting principle. You could have used combinations on the two greens. It would have been on your numerator, would have been 10, choose 2. Now you could also have done this indirectly by recognizing that this would be equal to 1, the total, minus the ones we don't want, which is the probability of having, the only thing that we cannot have with no green is, let me write this in English again. Excuse me, 1 minus the probability of all red, which would be red on the first, red on the second. So using an indirect approach is not a bad idea if you see it. In this case, because we'd already worked through so many components of the question, it wasn't a big deal. But these are designed for thinking questions. They're not complex algebraically, but you are supposed to read carefully and think. Now this one has long been considered a very difficult problem, and it really isn't if you stick with it. But it goes like this. At a family reunion, door prizes are to be given out. At one table in the community hall, 6 children, 3 teens, 4 adults, and 5 seniors are seated. Now this is at the one specific table. And then it goes on that the 3 winning tickets for the door prizes are held by 3 different people at this very table. Find the probability that the 3 winning tickets are held by 3 people in the same age group. And we'll take this one, we'll decimalize it to the nearest 1/100th. Now, as always, I'm going to start off with the fundamental counting principle. And I may abandon it because it may turn out to be too much work, but I will try to get a sense of what's going on. And for this question, because they're going to be held by the 3 people in the same age group, the possibilities are that it's 3 children. Or it could be 3 teens. Or it could be 3 adults. Or it could be 3 seniors. Any one of these possibilities is okay. And to get the 3 children, this would mean we'd be dealing with the probability of getting a child on the first, a child on the second, child on the third, plus, then for teens would be the probability of a teen on the first, teen on the second, teen on the third. Again, feel free to shut me down at any point and do it on your own. 3 adults would be adult, adult, adult. And 3 seniors would be probability of senior, senior, senior. And then you just work your way through this one. Now the first draw, you have these, 6 plus 3 plus 4 plus 5 is 18 people. The probability of you getting a child on the first draw would actually be, there's 6 children, so 6 out of 18. The probability of getting a child on the second draw, well, there's 5 children left out of a total of 17. A child on the third draw, there's 4 children left, and then there's 16 people to draw from. And then let's keep working our way through it. I'm not going to actually get the answer for this because it's going to be a little more work than I like, but we do get a sense of what's happening. Now for teens, there's only 3 teens, so the probability, starting all over again, of selecting a teen is 3 out of 18. Then a teen on the next is 2 out of 17. Teen on the next is 1 out of 16, and you get the idea. And then you work each one of those out and add them together. Very reliable. But your sense may be that it's turning into quite a bit of work. So if you can shortcut this by using combinations, you're well advised to. So using combinations, we would tackle it a little bit differently. The probability of having 3 of the same age group, not a very snappy way to word it, would be equal to, well, on your denominator, often the easiest place to start. You're choosing 3 people, 18 choose 3. And then we know we're going to be adding them together because we're dealing with, the children, then the teens, the adults. It's or, can't be one and the other. To get the children worked out, it would be 6 choose 3. So this would represent children. How many ways can you select 3 children out of a group of 6? To get the teens would be 3 choose 3. To get the adults would be 4 choose 3. And then finally the seniors, 5 seniors would be 5 choose 3. So it's a little faster than the other method. Now if you're going to do this on your calculator, make sure that you press enter once you're through on your numerator. And then divide by 18 choose 3, because otherwise your calculator, I know you know this, will just divide out the last 2. So we would go 6 choose 3, don't stop, just keep going with it, plus 3 choose 3, plus 4 choose 3, plus 5 choose 3, enter, just 35 by the way, so that's an easy one, I'll even write it down. And then 18 choose 3 is 816. So this would have made a nice fraction, but let's decimalize it just for the fun of it, and the question did ask that.